Okay, I was looking at this resistor board here, and I noticed some things that I hadn't noticed before. One was this um, wire wound resistor. You see here it's all deteriorated. The insulation's off of it. It's definitely not going to handle the wattage it was designed to handle. It is attached. Goes from there to here. Okay. But it got really hot at some point and deteriorated, and half of the insulation is gone. That's a low resistance resistor, low ohm resistor, and they didn't have low ohms back then, so they used wire around just a wire coiled as a resistor, and it would handle the wattage. Okay, so it's sort of like these. This one is bad. So I noticed that, and I missed it before when I was looking at the resistor board, so I wanted to show that. The other issue is this capacitor that this guy put in here. It's 12 microfarad, 475 working volts DC. You notice in there that he soldered it to the ground of this capacitor here, to the ground of it, using line cord as a wire, which is really strange in and of itself. But that is a very bad solder joint. You see all that big clump of solder? You see how close it is to the chassis in between the two black washers that insulate these two capacitors? They're insulated from the chassis. They don't touch the chassis. Well, that big clob is too close to the chassis. It's a bad solder joint. Definitely shouldn't be there in the first place. Okay, there's another issue with this resistor, and that is he has the positive side of the resistor going up to this top capacitor. Now you notice this one does not have a black insulating washer under it. It has a metal washer under it because this one is grounded directly to the chassis. These two are isolated from the chassis. Basically, that means they float above the chassis with voltage. This one actually connects to the chassis. And look at this. This is a line cord going all the way from one end of the radio to the other. First off, you shouldn't use line cord, but okay, that's fine. It is copper wire and it is high enough gauge. But the second thing is, why run a wire all the way up there to solder it to a ground terminal? There are ground terminals all over the place. There's a ground terminal here on this bolt. There are ground terminals all through this. Half these resistors go to ground. Half of these connections go to ground. There's ground connections all over the place. You didn't need to run this wire all the way up there to connect it to the ground on that capacitor. He could have connected it to the chassis anywhere, or to any ground terminal in this area. Anything that's grounded would have worked. I mean, all he did was connect it to the chassis, in effect. So we got this long dangling wire on this capacitor. Anyway, there's one other issue with this capacitor that I wanted to show you. I was able to pull up the schematic. And when we look at the schematic here, there's a couple things I want to show you on this. This is the three capacitors, C31, C32, C33. See them? Yes, they're right there. You can see them. C1, 31, C32, C33. Okay, they come off the rectifier, off the transformer, connects to the rectifier, comes off the rectifier, actually right off the transformer, and comes over to C31. And so they come to C31. C31 goes through a coil and connects to C32, which connects to all of the grounds are connected together. In this case, anodes are connected together. And I don't think that's right the way they got them in there. I think they got them in backwards, but anyway, I'm going to verify that. But regardless, okay, so we got these three capacitors. This one goes to ground, which is the one I showed you at the top, C33. That's this guy up here that has a wire and no insulator. It's grounded. Okay, so this one is grounded to ground. These two do not go to ground. They go, this one goes to ground through a 60 ohm half watt resistor, R22. That goes, so basically in the schematic they just jumped it across here because this is ground, and they're just showing you there's one that comes from here and goes to ground. Same place this one goes, ground. Okay. There is nothing that goes from this capacitor, C32, to C33 except this coil and this resistor that goes to ground. You can think of these as not really connecting together. They just happen to be connecting both to the chassis. They can connect to the chassis anywhere. This guy, this resistor, doesn't have to go here to go to ground. It can come up here and connect here to go to ground. It can go anywhere. You can come up here and connect to here. It's the same place. It's the same thing. Connecting to any of these points, you're connecting it to ground. So basically there's a resistor from this side of the capacitor that goes to ground. That's it. That's all that's on this side of the capacitor. Okay, is a resistor to ground. This one doesn't go to ground at all. Okay, it's floating. If you scroll up on the circuit diagram here, you'll see it goes into a coil, goes over here between these two resistors, comes up here to this 1 megohm resistor, and that's as far as it goes. It goes to that resistor. It comes through here. It goes between these two resistors. It connects between them. Comes over here, connects to this coil. That's as far as it goes this way. Comes up here, and it does connect to this capacitor. So these two are connected together through this wire, and it goes through the same resistor to ground. That's the only way it gets to ground is through this 60 ohm resistor. And it comes over here to the center tap of this coil, and that's it. It doesn't go directly to ground. It goes through a resistor to ground. This one goes through a resistor to ground. This one goes directly to ground. These two are insulated from ground by a 60 ohm resistor. This one is not insulated from ground. It's the top one. It goes directly to the chassis. Okay, so you see that. So the only thing that goes from C32 to C33, if you wanted to run something between those two directly, they're far apart, you wouldn't do it. But if you did, it would only be this resistor. So this is C32 here. This is C31 here. He's got this capacitor going from C31 up to this C33 to ground. There is no capacitor coming off C31, off the negative side of C31, going to ground. Here's C31. There is no capacitor on C31 at all. There's that coil. There's the transformer, comes in from the transformer, goes to the capacitor. From the bolt side of the capacitor, that's at the black insulator, comes down, goes to the center tap of this part of this coil of the transformer. Comes down here. You can go up through a 60 ohm resistor and get to ground, but that's all you can do. It does connect here. So these two connect together right here, okay? So the only thing that goes from here to ground on this capacitor, if anything at all, is the 60 ohm half watt resistor. Down here goes to a coil, over there, as we said, goes to two resistors. If we go all the way through, it goes to another resistor up here, 1 megohm that we looked at a minute ago. Nowhere does it go to ground, and nowhere does it have a 60 microfarad, a 16 microfarad, 12 microfarads. Nowhere does it have a 12 microfarad capacitor on it. It does not even have a capacitor on it. It It goes by this one. It's not connected here. There's no dots. It connects to this 1 megohm resistor. There is no capacitor on the negative side of C31 or C32. Zilch. None. So what is this 12 microfarad capacitor doing here? It's doing absolutely nothing that the schematic says that it needs to do here. This was put in, maybe there was a hum, maybe one of these capacitors was going bad. Somebody threw this in there and it seemed to get rid of some of the hum, and they just left it in there with line cord. Well, that's coming out. We're taking that out. It don't belong there. It's not part of it. Now, we do want to track down the capacitor that goes, the 60 ohm resistor that goes from here to ground. We need to find that somewhere in here and make sure that it is in there and that it is working. And that's this resistor here. We need to make sure it's there. And I pretty sure I know where it is. Okay. Now we got another issue that I found in the schematic. And this one's from the manufacturer. It's actually a change. See this coil that goes from H around through here and over to H, and in the center we have a center tap. Okay, you can see that there's a center tap on that coil. The two pilot lights go across this, and it has a center tap that goes to ground. So from here to ground there's a voltage, and from here to ground there's a voltage. And across it are these two dial lights. And that's the H coil with a center tap. Okay, if we go to the transformer, here we see a picture of the transformer. Now, notice a few things here. Here is our H that we were just looking to. There's one H there, there's an H there, and this is the H center tap. This is the one that connects in the beginning, in the middle, right, between that coil. Okay. If you look here, you see this capacitor goes up at an angle, doesn't go straight from here to here, it goes up at an angle to there, right? Down from it, we have a resistor that goes across these two, this F coil. This is an H coil, this is the F coil, and it has a center tap on it, okay? So you see that. And then we have a MDAC, or an MOAC coil, rather. Here to here, okay? So, a couple things. If we look at this capacitor, it goes up at an angle. If we come straight down, we see this double F coil with the center tap. So if we come here, and if we look at, I got it on its side, but if you look at this capacitor, this is the one. It goes up at an angle. It starts here at the bottom of the transformer, and it goes there. It doesn't go over there. It goes up at an angle. If we come straight down from it, we find the F coil, which is right here, and it has a resistor with a center tap. Up here we have our H coil, right across from the capacitor, and I'll show you that on the chart again in a minute. And this is the center tap for this H coil. Okay, when I check ohms from here to here, I get resistance. When I go from here to here, or here to here, I get nothing. So this is no longer a center tap connected in between here. I'm thinking they changed it at some point. They changed the model, or they got a different deal on transformers, or they got a bad batch of transformers where the center tap wasn't connected. So instead of using this coil with the center tap, they threw this resistor across here that had a center tap, and it got hot, and that's what happened to it. It burnt up. So basically, this is the center tap. It's taking the place of this center tap that's not connected internally in the transformer. And how do I know that's true? Okay, bear in mind this resistor with the center tap, that's standard. That's over near this capacitor, C31. Come back here. Here's C31 right here. Notice, there's the H. There's the center tap. there's no resistor like this across this with a center tap. And this is saying that it's a center tap, but there's no connection between this. So this one of these that's over here that's broken was added after the schematic was made. Most likely because they got a transformer where this was not connected internally. So they put one outside. Okay, and that's the manufacturer did that, and that's fine. But they might not have put the right value to make up the resistance that should have been between these. And that might be why that got hot and got burnt. I don't know. But that's what they did. Now, if we go to the, and you see that that's directly across from this capacitor. So you know we're talking about the same one. Now if we go back up to the schematic and look again at the transformer, here it is. There's the H. There's the center tap that's not connected for whatever reason. Fortunately, from here to here, across this coil, we have continuity. There's no breaks in this coil. If anything, there's a break in this wire that goes to ground. But that doesn't matter. They put the resistor on the outside since it wasn't working on the inside. And these are for the dial lights. These wires are sticking out here may continue to go to the heater elements of the tubes. See these H's? HH, 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 HH. That's the heater strings. They usually connect, well in this case it's 6 volts. On some radios, the later model radios, they go in series. The power will come into one, come out of the other. They don't draw them in. It'll come into one, come out of the other, come into one, come out of the other. And just like Christmas tree lights, if one of them burns out, all of the tubes go out. That's newer radios, but this is an older radio. And so what they did is they used all 6-volt tubes. And the 6 in the front means 6 volts for the heater. These dial lights will be 6-volt lights. And this goes to the heater of those tubes. Here it's called filament, F and F, F and F, but it's the same thing as H and H, F and F, F and F, H and H. It's the heater string. Now these filaments, the reason they're calling them F and F and not H and H is because they're connecting across this filament wire here. And the center tap of this resistor is going to the speaker field, the field coil on the speaker. This is all working, at least here it's working. I haven't checked the field coil yet. So for these tubes, these 3, okay, the filament string is from here. For all the others that have heaters, it's from here. The only thing I'm concerned with is this ground not being working. And so what they might have done is, since this might be a defect inside the transformer, they might have put one of these center tap resistors here across here and ran the center to ground, which would do the same thing as what this coil would have done. It's a voltage divider. Half the coil voltage is here, the other half of the voltage is here. So if you're working on one of these, you can say, for instance, let's say this is 10 volts, or 6 volts. Let's say this is 6 volts, which it probably is. There'd be 3 volts here, and there'd be 3 volts here, which would be 6 volts. So what they did is they put one of these resistors in, half the value of the resistors here, half the value of the resistors here. There's 3 volts here, there's 3 volts here, same thing. And then they run the center to ground. That would be that. And since that seems to be the case, then this is bad, because half of the filaments on these tubes could be blown if this is not the right amount of voltage on this side. We know it's right here. This doesn't look good. So we got to repair this in order to safely power this unit up. And you see why it's so important when you're working on these to follow these things through. Because if you did not follow this through and you powered it up and this coil was to break, you could burn out the filament on every single tube at one shot, because they're all connected in parallel. Now, I don't know, the tubes may already be burnt out. I have to check them. I haven't gotten to that point. I'm still looking at the circuit. This bothered me. I needed to find it. And I also found, in the process I was looking, I found this resistor. The interesting thing that I found here is that this half of this resistor here comes over here. You can see it on this side of the board. It's this brown wire here. This brown wire here goes up here into the back there and connects right there, right above my fingernail. Connects there to the same place this wire connects. And if you trace this wire over here, lo and behold, look where it goes, to the center of this guy. So we have a burnt coil resistor here that's connected to a burnt resistor here that goes to the filaments of all the tubes. Now you see why I didn't power this radio up without finding out about this. And in the process, I found out about the center tap not working, and that's probably why they put this here. Now, my question is, did they mess up even further when they put these capacitors in? Because they're showing these capacitors negative. Well, this one is negative floating here to this floating ground, and so is this one. No. Yes, so is this one. The negative is on the floating ground here. That's this one up here. And the negative on this one is on this floating ground here. But they have the positive of this one going to the ground up there, which makes it seem like this chassis is positive in respect to these grounds here. And that's possibly the case, but this don't belong here, so it doesn't matter if this is in correct way or not. It just doesn't belong here. It's not in the schematic. And what did this do? Did it pull too much voltage on here, pull more voltage than it's supposed to, draw too much current when these things were going bad and burn out these? Or is this backwards and shorting out the ground, drawing a whole lot of current and burn out these? I don't know. I mean, you know, I'd have to spend some time looking at the schematic. But the bottom line is, this is not good, this is not good, and this doesn't belong here. And those things make me nervous when I see that these go to the heater. So, next thing is to fix these so we can power this radio up. And temporarily what I might do is calculate the resistance of this and throw a resistor across here, 2 resistors across here with a center tap. Take this wire off the center tap of this and put it on the 2 resistors I'm going to put in. Now we can get low ohm resistors, so I'm going to replace this with a low ohm resistor. And since this is going to here, going to the center of this, which would normally be this, going here, and it's also going to this burnt resistor, I can probably safely say that this is the 60 ohm resistor to ground, which would be this one here. And to verify that, which we will do right now, we will connect one probe to the chassis and one probe, this probe, we will, if I can get it out from underneath some stuff, we will check that resistor there. Okay, so let's put this on continuity, get it to beep. Okay, now that See that? On this side, look what I'm getting. 60 ohms, 57. On this side, I'm at ground. This side goes to ground. This side is 60 ohms. That 60 ohms wire is, I'll get to it. This is the ground side. It goes back here, connects to that, which comes over here, connects to this. And you see why I was saying that if he needed a ground for this, he didn't need to go way up there. He could have connected it here, but it don't belong here. He could have connected it here. Could have connected it here. There's all kinds of connections for ground all over the place. Could have connected it in there, but right here. He could have connected it right there if he needed ground. But this is a problem. One other thing that I wanted to touch base on is this setup here. Whenever anybody does work on a radio, especially when you see sloppy things like that, you definitely need to check everything that's been done. You can't assume that just because they got it playing, that they got the radio playing correctly. Look at this resistor here, which they have going across here. It's, if the camera will focus there. There you go, you can see that they have a 25 ohm resistor, 10% tolerance power resistor across those two lugs. Here, this one doesn't even have any writing on it. And we don't know what it is. And they got that across these two lugs of this resistor bar, wire wound resistor bar. If we check the resistance across this one, I can get in there with one hand, okay. Here. And boy, having that lead that close to that other one is not good. But if we check the resistance across that one, that says 25, we get 37 ohms. All right, it's dropping a little bit. It's about 36 ohms on a 25 ohm resistor. So that resistor is already way out of tolerance. At 10%, it can't be more than 27.5. If we jump across this unknown resistor, we get 1.48K, so 1.5K, 1500 ohms, and that's probably what that is, 1500 ohms. These resistors, though they're old stock, they were pretty good, and they held up pretty well. So 1500 ohms. So we got 37 ohms, 1500 ohms, and then from here to here we got over a meg ohm. So we got a problem there. I don't doubt that coil wire wound resistor has gone bad, but bear in mind those measurements. If we come to the schematic here, you'll see the three sections of that resistor. The first one here goes, the resistor starts at ground, basically. One end is tied to ground, and it's a tapped coil. The first one is 10 kiloohms, or 10 milliohms here, which is, M is the old designation for what we call K today. So it's 10K. Not 25 ohms, not 1.5K, but 10K from here to here. So, okay, well, maybe that's the part that's dead, right? Well, no, I don't think so, but if we look at the next section of it, it's right here. Again, it's 10K. And the final section is right here, and it's 4K. So we have 4K, 10K, and 10K making up that resistor. We don't have 25 ohms, nowhere. That resistor makes no sense. Now again, somebody might have put that in there because it made the radio work, but that's not according to the specs or the schematic diagram, so that's bad. This here is not working. It's charging a capacitor, but it's definitely not good. So come across there. I'll just stick it on that wire. Okay. And you see we're over 1 meg. So we're over 1 million ohms. So that's just the capacitor itself that it's charging. If that leg was fine, let's assume that this is the 4 K ohm resistor. If that was 4K like it's supposed to be, that capacitor couldn't get up to 1 meg ohm charging. It would max out at 4K. So that's not good. Anyway, basically what we got going on is a lot of issues with this radio receiver. It's a very complicated receiver, obviously. This is just the bottom side. It has 13 tubes counting the I tube. This is not a simple receiver to work on. It has 3 IF cans. I can't even get in there to check the coils on them, but we'll check them as we go when we troubleshoot the circuit. But for right now, I just pointing them out. There's 3 big IF cans on the top part of the schematic. So the best way to repair a radio of this complexity, and let me just give you a little scroll over here. Look at what we got going on. Look at all these coils. The highest one I found is L13, there's L12. Anyway, 13 coils going across here. These are the tubes on the top. It's got 3 IF cans, low end, intermediate, and high end. The 3 IF cans. It has complicated circuit, a whole lot of information here. They dash lined this section out here. This is the sensitivity control section. So you have some tuning here to tune the sensitivity in these between these 2 IF cans, and then you got a final IF can over there. You have all these variable capacitors in these coils, just a lot of them. They're all going to be tuned. You got all of this here. Now, fortunately, they give you the voltages on the tubes. We're supposed to have 200 volts on the plates of these tubes, 80 volts here, on the grid of that one, screen grid, 200 volts here. So they give you the screen grid voltages. This one's 6.5, well, the screen is 80 on this one. Here, 80. So they give you the voltages. You know, that helps. But it is a very complicated radio. It's a lot of switches. All over the place, there's switches. So the best place to start when you're working on a radio, let me zoom out a little bit here, is here at the power supply. And first thing you want to do is get the power supply working. So I'll probably pull some of the tubes to disconnect the power supply, but you can, and for the safety, although I tested some of the tubes, I tested these and they were weak. Actually, they were bad, a couple of them. So I don't know what happened there, but probably what they've worked on, what they did, caused some over voltages. But first thing we're going to do is pull the rectifier tube, and we're going to check the voltages on the transformer. I have fears that this one will have no voltage, but we're going to check the voltages on the transformer. Then we're going to pull these tubes here and check the voltages on these pins with the tubes out and see what we're getting from the rectifier. Are we getting our 390 volts? That's the first thing we'll check. Then we'll check the voltages across each of these. And in the process, we'll be checking these capacitors by checking these voltages here and seeing how smooth they are. Once we get the power supply working good, then we know that we have the correct voltages going to these tubes for the plates and the screen grids. Then we can go through and check them, put them back in and check them and see what voltages we get there. But I want to get the power supply working first. That's the first place to start. I mean, some people would start at the antenna and work toward the front end, but you always start with the power supply and then go to the antenna and work toward the front end. You can also work from the back end. You can start with the power supply and then go to the speaker and work back from the audio output tube, which is hiding. Well, anyway, you can work from here it is. The output tube is right here, these 245s, they're in the power section. You could start from there after you get the power supply going, and you could start from the coil, work your way back through the the output section here, up through the detector, first the audio frequency amplifier here, back through the IF tubes and the IF amplification here, back to the oscillator and translator, oscillator, mixer tube, back to the RF radio frequency amplifier circuit, and then back to the antenna and to adjust the coils. That's one approach. Another would be to do the power supply and do just the opposite. Come in at the antenna, check for the signals through the RF, skip over the coils temporarily, go through the IF chain, make sure everything's okay, come to the output. But I prefer to do it from the output side, and the reason being is once you get the power supply working, then you can just touch the grids of the output tubes, and you should have, inject the signal, you should have a strong output coming from the speaker. If you have that, then you know the output stage is good. And then if you can even go from the output stage, verify it's good, verify the power supply is good, and go back to the antenna and then work through. That's fine too. But it's so easy to check the output stage, so I prefer to do that. Also, this is where your power is. This is the low voltage, high current part of the circuit. You got 375 volts high voltage on the plates, but you got low current. And when it comes through the output transformer, it's converted from high voltage low current to low voltage high current. So you want to make sure that this works. You want to make sure you have the power supply. You want to make sure you have the amplification here in these two tubes. And you want to make sure all that's right. And this is an unusual output. I like it. It's two 45As, and they are actually in parallel. The grids are connected together, so the input signal to the grids are in sync. The output is in sync because they're connected together. It's not a push-pull configuration. So we will start with the power supply. That's the most important, and actually the most critical is this transformer. So we're going to start with that. So I'm going to go ahead and set up, and I'm going to take out the rectifier. I'll probably take out all of the tubes so we don't hurt any tubes while we're going through, and we'll check the transformer. Then we'll check the voltages going to the actual tubes. Now bear in mind, when you work on a radio like this, especially with a transformer this big, you're looking at some really high voltages that can kill you. These are this is a very dangerous set. If you do not know what you're doing, do not work on a radio like this. This sources out 400 volts and AC, and that's a lot of voltage. So be very careful working on these units, and take all the precautions you can. Never put but one hand anywhere, and even then you're at risk. So be very careful you don't come across the AC lines in the circuit, or the DC. I mean, we're talking high voltage DC, 375 to 400 volts DC after it's rectified through the rectifier tube. So be very careful. Okay, gonna set it up. Excuse me. Okay, what I was doing is checking the transformer here, and I pulled the rectifier tube out. I went to check the rectifier tube, and the filament's blown. So that's probably because it was run without pilot lights in it. That always will blow out a filament rectifier, or it could be because of the way they rewired this thing. It just burnt it out. But I was concerned about the voltage, and I wanted to show you why you got to be extremely careful. I have no rectifier. I'm checking across the output of the transformer, the B plus line, or what would be the B plus line, and you see I have 516 volts AC across the pins of the rectifier plates. I'm only at 82 volts. If I crank this joker up to what it should be, around 115, 110 volts, I'm already over the limit of my meter. You hear that major beeping? That was my meter saying, you're going to burn me up. I have way too much voltage. So you've got to be extremely careful working on a radio like this. Okay, let me go ahead and pull that off of there, and we will check the rest of this transformer, because I'm concerned about this here. You know we're going to have a lot of voltage there. Let's see if we're getting anything across this. Oh, and I pulled that capacitor out, obviously. Okay, so if I bring the voltage up here, and we're on AC volts, you see that the voltage is climbing. That's good. So we do have voltage on the filament string line. We got over 5 volts, so that'll drive the 6 volt filament string. And then the next voltage string is this one, which is the filament for the other tube. And let's see what we got there. Okay, we got voltage coming out of there too. So, a couple volts coming out of there. All right, so that's the F line. So we do have voltage on both lines. I still don't know about that resistor, but we have voltage on both lines. However, the rectifier tube is bad. I'm going to have to order a rectifier tube. Let me shut this off. And here it is here. And of course I checked it on my meter, and it didn't do nothing. So I know the filament's bad. So let's check that here. We'll put this on ohms. Come across the filament. And on these 4-pin tubes, you can tell what the filament is. It's the two thicker pins, and I'll show you that. So you see we have no continuity at all. Open circuit. open load. So this rectifier tube is shot, this 5Z3, and there you go, there you can see the pins, and you can see how these pins are wider, thicker than these pins. They'll only go in a socket one way because these two are bigger than these two. And that's the filament, that's the plate. And there's no continuity in the filament, tube shot. So, since I'm gonna have to order that tube, I might as well go ahead and check all of the tubes and make a list of all of the tubes that are bad, and give that feedback back to the owner, and go from there. Thanks for watching the video. If you found this video helpful, please consider giving it a thumbs up. I appreciate any support, and stay safe. Thank you.